Welcome back, ladies and gentlemen. Today we're going to go through day 1 of section 2.1. This is the first day of our chapter 2 material. And we would be looking at measuring position, percentiles, cumulative relative frequency graphs, and measuring position with z-scores. Now, by the end of this video, you'll be able to find and interpret the percentile of an individual value within a distribution of data, estimate percentiles and individual values using a cumulative relative frequency graph, and find and interpret the standardized score, z-score, of an individual value within a distribution of data. As usual, this is a lesson that you should attempt once we complete this lesson. Let's dive right in. As I said, we are doing section 2.1, day 1, describing location in a distribution, percentiles, and z-scores. All right, so we're going to start off with an example. There are 25 students in Mr. Tabor's statistics class. He gives them a first test worth 50 points. Here are the students' scores. We have a 35, 18, 37, 38, and so on. All right, now Emily's score is 43. How did she perform on this test relative to her classmates? All right, a dot plot displaying the class's test scores is shown below. The distribution is skewed to the left with some possible low outliers. As you can see, most of the data is clustered up here towards the top, and there are a few scores moving off to the left from the cluster of data. All right, so from the dot plot, we can see that Emily's score is above the mean balance point of the distribution. We can also see that Emily did better on the test than most other students in the class. So Emily's score is right here. All right, so that would be about 43. Now, how do we actually determine how she performed on this test relative to her classmates? All right, first thing that we're going to look at is measuring percentiles. All right, so you can read this information on pages 91 through 94. And one way to describe Emily's location in the distribution of test scores is to calculate her percentile. Now, what is a percentile? What does a percentile measure? And how can you be in a percentile? Now, the definition, the pth percentile of a distribution is the value with p% of observations less than or equal to it. So equality is an option here. Now, before the course and exam description for AP Statistics was changed back in 2020, we used the definition of strictly less than. Now, since 2020, we are using the definition for less than or equal to that value. Right now, some people do define the pth percentile of a distribution as the value with p% of observations less than it, so that is still a valid definition. This doesn't really matter in continuous distributions because the exact value doesn't really have a probability value, but it would matter in discrete distributions. All right, the College Board framework has chosen the less than or equal to percentile definition for the AP Statistics curriculum in its current format. All right, now, when you're talking about percentiles, percentiles are specific locations in a distribution. Observations are at the pth percentile, not in the pth percentile. Right? You are at a location. You are not inside of the location. All right? It's a specific location. You are at a specific set of coordinates if you are using GPS. You are not in the coordinates. All right? So using the word at is necessary when you are interpreting these. All right, be careful with your language. All right, now for our first example, let's refer back to the scenario at the beginning of our notes using the dot plot representing the class's test score distribution. So this is the dot plot that we had at the top of the page. What is Emily's percentile in the class's test score distribution? Now, if we take a look at Emily's test score, there are only 4 students who scored above Emily, which means that her score would be the 21st from least to greatest as you're going through the distribution. So if we're looking at less than or equal to, there are 21 scores less than or equal to Emily's out of the 25 student scores. If you divide this, you get 0.84. Now this would be the proportion for Emily's score. And if we turn this proportion into a percent by multiplying by 100, 84% of scores are less than or equal to hers. That means that Emily is at the 84th percentile in the class's test score distribution. Now, if we find the percentile for Jacob, who scored 18 on the test, right? 18 is down here. There's only one student who scored lower than Jacob. His score is the second ranked out of the 25. So if we look at 2 divided by 25, that would be 0.08 as a proportion. Multiply by 100, and you have 8%. So Jacob scored at the 8th percentile on the test. Notice the way that I worded that. He scored at the 8th percentile. Maria's test score is at the 48th percentile of the distribution. Interpret this value in context. What score did Maria earn? Now, if we look at Maria's being the 48th percentile, 48 out of 100 is 0.48, and 0.48 times 25 is 12. Now, why did I do this? Percent actually has a meaning, right? Percent means out of 100. So you have to take the 48 out of 100 in order to look at the proportion that it came from. And we multiply proportions by the total to figure out how many numbers we need to look at within the distribution to arrive at the one that's at that particular percentile. So the 12th number in the distribution, when it's ranked from least to greatest, is going to be where Maria's score is. So Maria scored greater than or equal to 12 of the 25 students. And if we look at the 12th number, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? Maria would have earned a 37 on this test. This would be 36, 37, 38. This blank here would be 39, and then we're at 40. That's how I know that this is 37. All right, so Maria earned a 37 on the test. All right, the interpretation is the 48% of students in the class earned a test score less than or equal to Maria's. That's interpret this value in context. What score did she earn? That's what I was doing right here. All right. Keep track of when there are multiple things requested of you in a problem. All right, let's take a look at the next page. All right, now commonly calculated percentiles. They're specific values that you've looked at previously. All right, if you remember back in section 1.3 within our material, we looked at the median, first quartile, and third quartile. The median is roughly the 50th percentile because about half of the observations are less than or equal to the median. The first quartile is roughly the 25th percentile of a distribution because it separates the lowest 25% of values from the upper 75% of values. Likewise, the third quartile is roughly the 75th percentile. If you think about what quarter percentile means, quarter of all the percentiles possible, 1/4 is 25%. And because you're looking at a percentile as less than or equal to, the percentile itself refers to the left side of the percent split. So 1/4 of the data split off from the remaining 3/4. That's why this would be the 25th percentile. 3/4, 3/4 is 75%, which is why it would be the 75th percentile. Now, a little bit of caution when you're interpreting these. A high percentile is not always a good thing. It is with test scores typically, but consider the context to determine whether a higher or lower percentile is preferable. For example, the time it takes to finish a race, golf score, car mileage, lower is typically better. The less miles a car has been driven, oftentimes the more it's worth compared to other vehicles of the same type and the same vintage. The time it takes to finish a race, the faster you are, the more likely you are to win. Golf score, negative scores are actually better because 0 is perfect par. Above 0 would mean that it took you more strokes to actually finish a hole versus negatives where you got a birdie or an eagle as you're going through. Now, cases where higher is better would be like gas mileage, so how many miles you can go for a single gallon of gas. Goals scored in a soccer game, more is better. And long jump distance, further is better. So you have to consider context to know which type of percentile is actually better. Now, cumulative relative frequency graphs. Cumulative relative frequency is when you're literally adding up the relative frequencies as you go along. So what is a cumulative relative frequency graph? Do you need to be able to make one? For our definition, a cumulative relative frequency graph plots a point corresponding to the percentile of a given value in a distribution of quantitative data. Consecutive points are then connected with a line segment to form the graph. Right, now the meaning. It's a graph that plots the values of the variable on the horizontal axis and the corresponding percentiles on the vertical axis. Now, something to note, you do not need to be able to make this graph. You only need to be able to use them forwards, value to percentile, and backwards, percentile to value. So for our second example, here is a cumulative relative frequency graph showing the distribution of points scored per game for the 486 NBA players in 2016 to 2017. Now note that PPG stands for points per game. We have points per game listed here, but then in letter A it says Pau Gasol scored 12.4 PPG, points per game. About what percentile is he at? Interpret this value. So he is at approximately the 77th percentile. If we look up from about 12.4, 12.4 is almost midway between 10 and 15. Right? So if we follow this up and then we follow it across, this is at about 0.77, I would say. 0.75 would be directly in the middle. This is a little bit higher than that. It's a little bit difficult to tell whether it would be 0.77 or 0.76, but that's why we say about what percentile. As long as you're close and it seems reasonable, then we would accept it. So he's at approximately the 77th percentile. This means that approximately 77% of NBA players in the 2016-2017 season scored less than or equal to 12.4 points per game. Now, another common thing that you're asked with these kinds of graphs to be able to interpret them is, for example, to estimate the first quartile for this distribution. Now, since the first quartile is at the 25th percentile of the distribution, we want to go to where we would have directly between 0.2 and 0.3, that would be 0.25, that would be our 25th percentile. I follow this over to the right and then follow this down, and I kind of separated this off with tick marks to see approximately what number this would be. And it looks like this is at about the 4th points per game. So first quartile is about 4 ppg. Let's take a look at the next page. And we are still continuing on with this same example. And I'm going to move this underneath here so that we can actually look back and forth between them. All right, so sketch a relative frequency histogram of these data. I made a table here with PPG and then relative frequency. And what I did is I kind of estimated the point at which each of these intervals, what percentile each of these intervals were at for the cumulative relative frequency. So this first one I estimated 5 to be at about 0.32, which is what I have written here. 10 I estimated to be at approximately 0.69. Now 0.69 is inclusive from 0 all the way through to 10. I just need from 5 to 10. 0 to 5 was 0.32, so I took the 0.32 away from the 0.69, and that gave me the relative frequency that accounts for from 5 to 10. So from 5 to 10, I had about 0.37. I kept going in this manner all the way through. I estimated that 15 was at about 0.87, that 20, if you followed along to here, was at about 0.93. I estimated that 25 was at about 0.97, and that 30 was at about 0.99, 35 was at 1. Right? And then each of those values I subtracted from the previous cumulative relative frequency so that I could figure out the change between each of those values for the interval relative frequency. Okay, so each of these subtraction problems represents one height minus the previous one just to figure out what was the actual relative frequency when you take away all the rest that came before it. So you're just looking at for that interval. And then I made bars at those heights for my histogram. So 0.32, this first bar from 0 to 5 is at about 0.32 in height. My next bar is at about 0.37 for height, and then 0.18 for height, and so on. It was kind of tricky once I got down to here because I had 0.03, 0.02, and 0.01. That was definitely a challenge. Right, now, where is the original graph the steepest? Where is it the flattest? And what does this indicate about the distribution? Now, steepest would be from 5 to 10. And if you look at that, that's also where the relative frequency for just that particular interval was the greatest. All right, so the highest proportion of the 486 NBA players from 2016-2017 scored between 5 and 10 points per game, while the lowest proportion of players scored between 30 and 35 points per game. That was when we had the lowest relative frequency because the graph was the flattest for this last interval from 30 to 35. All right, so that's what steeper means higher proportion. Less steep, flattest, means lower proportion within that interval. All right. And let's explore another scenario. Right, so Macy, a 3-year-old female, is 100 centimeters tall. Brody, her 12-year-old brother, is 158 centimeters tall. Obviously, Brody is taller than Macy, but who is taller relatively speaking? So that means relative to other kids of the same age, who is taller? According to the CDC, the heights of 3-year-old females have a mean of 94.5 centimeters and a standard deviation of 4 centimeters. The mean height for 12-year-old males is 149 centimeters with a standard deviation of 9 centimeters. All right, we'll be using this in future examples. So measuring position, all right, z-scores. A percentile is one way to describe a location of an individual in a distribution of quantitative data. Another way is to give the standardized score, which we refer to as a z-score, for the observed value. Now, what is the standardized score, z-score? How do you calculate and interpret a standardized score, or z-score? So for our definition, the standardized score, z-score, for an individual value in a distribution tells us how many standard deviations from the mean the value falls and in what direction. Now, I accidentally left off an N when I was spelling out mean. Obviously, I need to proofread this just a little bit harder. But our formula is that z, meaning z-score, is equal to the value from the distribution that we want to look at minus the mean of the distribution divided by the standard deviation of the distribution. And the interpretation is that this value is whatever the answer is to the z-score, that number of standard deviations above or below the mean, depending on whether the z-score is positive or negative. If the value is higher than the mean, then your subtraction is going to turn out to be positive, which means that you're that many standard deviations above the mean. If your value is less than the mean, then this will turn out to be negative, and a negative z-score means that that's how many standard deviations below the mean the data point falls. All right, now, do z-scores have units? And what does the sign tell you? What can you use z-scores for? Now, we just went over what the sign tells us, but no, z-scores are not measured in the same units as the variable. If I have inches minus inches, my answer to that will be inches. If I divide by standard deviation in inches, inches divided by inches cancels out, and you no longer have units. So z-scores are not measured in the same units as the variable. We talk about z-scores in terms of how many standard deviations above or below the mean. The sign tells you whether the observation is above or below the mean. Positive z-scores are above the mean, negative z-scores are below the mean. A 0 is directly on the mean. Now, what do we use this for? We standardize observed values to express them on a common scale, kind of like calculating a percent where it's out of 100. Now we're calculating it to be out of the number of standard deviations, which is the average difference from the mean. All right, so let's return to our second scenario. And we still have Macy and Brody. And who is taller relative to kids of the same ages, Macy or Brody? So Macy's height was from a distribution with a mean of 94.5 centimeters and a standard deviation of 4 centimeters. The z-score is the value, in this case Macy's height, which was 100 centimeters tall, minus the mean divided by the standard deviation. So 100 minus 94.5 divided by 4. 100 minus 94.5 gave me 5.5 centimeters divided by 4 centimeters. No centimeters cancel. And I have 1.375. That means that Macy's height is 1.375 standard deviations above the mean for children of her age group. For Brody, the mean for his age group was 149 centimeters. The standard deviation was 8 centimeters. If we take his height, which was 158 centimeters tall, minus 1.49 divided by 8, we have 9 centimeters divided by 8, which is 1.125. This means that Macy is taller relative to other 3-year-old females because her z-score of 1.375 is higher than Brody's z-score of 1.125. And finally, Jordan is a 3-year-old female, and her height has a z-score of negative 1.5. Interpret the z-score and find her height. So this is going backwards. Jordan's height is 1.5 standard deviations below the mean height of 3-year-old females. This is the interpretation. Now finding her height, the z-score formula is z equals your observation minus the mean divided by standard deviation. Her z-score is negative 1.5. And if I fill in the rest of this, x is the observation, so x is the height I'm missing, minus the mean for 3-year-old females, because remember, we were told Jordan is a 3-year-old female. So x minus 94.5, and then divided by the standard deviation, which is 4. Now, what I did is I put this over 1 so I could cross multiply. You could also just recognize that you need to undo the division before you do any sort of addition. There's always a hidden set of parentheses that holds numbers together in the numerator. So negative 1.5 times 4 is negative 6. Add the 94.5 to the other side, and you have 88.5 centimeters. Jordan is 88.5 centimeters tall. This remaining example we will look at in class. And as always, try your book assignment before we get to class so that you can discuss with your classmates. I'll see you then.